What if the sun were replaced by another star? Stars are born in nebulae, clouds of gas and dust. As gas molecules and dust particles collide, they gradually explore and heat up under the influence of gravity, eventually forming. As protostars enter the early stages of stellar evolution, hot cores form and more matter accumulates, and the temperature continues to rise. When it reaches a temperature of about 15 million degrees Celsius, the star enters its primary phase and nuclear fusion begins. Stars spend about 90% of their lives in this primary phase. Scientists believe that in order to sustain nuclear fusion, a star must be at least 8.87% the diameter of the Sun. The Sun's diameter is about 1.39 million kilometers. Still smaller than the size of Jupiter. So why can't Jupiter be a supergiant? The reason is that Jupiter's mass and density are not enough, and the pressure and temperature inside are not enough to maintain nuclear fusion reactions. Usually, the larger a star is, the shorter its lifespan. A star the size of our Sun can live for about 10 billion years. A star that is 10 times more massive than our Sun will only last about 20 million years. So what happens when they reach the end of their life? About 97% of stars eventually become white dwarfs. Scientists recently discovered a tiny white dwarf with a diameter of just 4,300 kilometers and a surface temperature of 45,700 degrees Celsius. This white dwarf is only slightly larger than the Moon, about the same size as the distance from Los Angeles to Washington, D.C. But don't let this star's small size fool you. It's 35% more massive than our yellow dwarf Sun. In fact, the material from a white dwarf can weigh as much as a 5.5-ton elephant on Earth, making it the smallest star ever destroyed. It is also the most massive white dwarf. What's worth noting is that the rotation speed of this white dwarf is also very fast. It only takes 7 minutes to rotate once, 200 times faster than the rotation speed of the Earth. But if the Earth were in the active zone of a white dwarf, would we still be able to survive? When the Sun becomes a red giant, it will run out of fuel and turn into a white dwarf. So let's say the Earth is located in the habitable zone of a white dwarf. The white dwarf's light is strong enough to maintain some habitable zones, but it's too dim and its habitable zone is not. The habitable zone of a white dwarf is only 1% of the distance from the Sun to us, which is dangerous because gravity will keep the Earth tidally locked. The gravity of a dead white dwarf will cause a huge temperature difference on Earth. The planets closest to us, such as Mercury and Venus, may be completely destroyed. But this is just the beginning. As time passes, the white dwarf will gradually cool down, and its light will also become weaker and weaker. Its habitable zone will gradually move closer to the dead star. The decrease in light also causes high-energy radiation to surround us. If this happens, Earth will become like Venus, a planet with an atmosphere filled with carbon dioxide. How do you measure the size of a star? It turns out that scientists can estimate the size of a star by its surface temperature and its brightness, which is the amount of energy a star emits. To better understand this, scientists have developed a special chart to help predict the size of stars. This chart gives an estimate based on a star's temperature and brightness. Usually, we think of something as orange or red when it's hot, but the opposite is true for stars. Hotter stars will appear blue, while cooler stars will appear red. This rule also applies to some extremely rare types of stars. For example, W102 is a very hot star. It has only half the radius of the Sun, but its surface temperature is 35 times that of the Sun and it glows blue. In fact, there are many larger and more interesting stars in the universe. For example, HD 140,283, also known as Methuselah, is 1.7 times the size of the Sun, about 0.8 times the mass of the Sun, and 250 times the luminosity of the Sun. In fact, when scientists first calculated its age, they thought it was 16 billion years old. This is a huge contrast to the 13.8 billion year age of our universe. However, the corrected data still show that the star's birth date is close to the birth of the universe. The next star is a much younger star than the one introduced earlier, but it has some other characteristics that make it stand out from the others. The star to 136A1 is about 30 times larger than our Sun and is one of the brightest stars in the universe. If our Sun were replaced by to 136A, you would never be able to look at the Sun without wearing high-quality sunglasses. Its mass is 265 times that of the Sun, breaking the previous upper limit of the largest stellar mass by 150 times. This huge number makes it the most massive star known. However, despite its enormous mass, 2136A1 is still relatively small, much smaller than a blue-white supergiant like Alpha Centauri. This giant star is about 200 times larger than our Sun and at least 50,000 times brighter, but is only 19 times more massive than our Sun. Imagine if this giant star became our Sun, what would its light look like on Earth? Next, let's look at a typical red supergiant, Antares. The radius of this star is about 680 times that of the Sun, much larger than the distance between the Earth and the Sun. This means that if our Sun were to be replaced by Antares one day, the Earth and even Mars would be swallowed up. However, this red supergiant is so far away that it would appear as a blazing hot ball of plasma, burning with a mass 1,100 times greater than our Sun. But even this giant planet is no match for the largest star we know. Stephenson 218 is currently the most massive star ever discovered and the brightest red supergiant in the universe. Its radius is nearly 2,150 times that of the Sun. This number is unimaginable. The volume of the Sun can contain 1.3 million Earths, and Stephenson 218 can contain up to 10 billion suns. This speaks to the enormity of this star. However, this is not the maximum size a star can reach. Scientists speculate that in the early universe, a hypothetical quasar had been much larger, perhaps even as large as 10 billion km across. To give you a sense of the scale of the problem, if the new Enterprise probe took nearly 10 years to reach Pluto, it would take another 5 years to escape the nearby star's gravitational field. If the nearby star still existed, it would produce light comparable to that of a small galaxy, which would certainly be an incredible astronomical phenomenon. While there are many more fascinating stars in the universe than our humble Sun, it might be more interesting to see these giant planets from Earth. It might be more interesting, however, our lives could not survive in such an environment. Even the slightest change in temperature, radiation, or light fluctuations could spell disaster for us. Even if these stars were twice as big, hot, or bright, we would still be lucky. Because not only can we observe these giant stars through telescopes, but we can also spend every day peacefully with the Sun.